In this video, we are going to see an important element of the video cameras, the optical block. We will see different features, important features from the optical block, starting from the focal length that will be the focus of this video. Just for starting, we can say that the camera optical block is in charge of the optical electronic conversion, transducing light in the wall into electrical signal in our camera electronics. So, in this sense, is the first element of the camera that capture the light and guide the light toward the sensitive surface that is the sensor of the camera. The optical block is composed by different elements like lenses, filter wheels, and beam splitters. This optical block is usually the most expensive and critical. Why? Because to produce high quality images, high quality pictures, we need that optical block has a very high precision. What it implies in order to have a high quality, and this implies a high price. We will see different characteristics of the optical block: resolution, type of mount, focal length, aperture, depth of field, and aberration. We will describe especially in more detail the last four, and just for the first two, the resolution and depth of mount, I'm going to give a couple of comments. Regarding resolution, this is somewhat strange because you are used to or familiar that a camera sensor has a resolution. Higher the resolution, higher the detail that you can appreciate the capture image, the objects inside the capture image. Okay, but how is possible that a lens, that an optical block has also resolution? Well, just think that if you have a window and that window is somewhat dirty, the quality of the picture that you can see is not so high, is not so clear as the picture that you will see if that window is perfectly clean. Okay, this is the same for the lenses. Of course, we are not speaking about how dirty the lens is, but we are speaking about the purity of the crystal. We can have a very high resolution sensor, but if the purity of the crystal is not good, the effect will be the same as our lens will be somewhat dirty, and we can lose in definition in the capture image. So the resolution is also a very important feature for the camera, for the optical block. Regarding the type of mount, is simply that we have different mounts to connect the optical block to the camera. Well, let's start then from the focal length. The focal length measures how strongly this system, that optical block, can converge or diverge the light. Also, from a more technical point of view, we can define the focal length as the distance from the lens optical center to the principal focus or focal point. This is the optical center and the focal point or principal focus. So the focal length is precisely this physical distance. And how can we define those points, optical center and focal point? Well, the optical center is a point over the axis of the lens in such a way that any ray of light passing through this point does not suffer any deviation, any refraction, any blending. It's just it continue its direction from this point. There can be also another not a straightforward rays, but with some kind of inclination. But the point is that any ray that pass for this optical center do not deviate from his initial trajectory, unlike these others that are blended in order, I will see later, to focus all the different rays that coming from the same object to the same point to produce a sharp image. Regarding the focal point, is precisely the point at which different coherent collimated rays coming from the same objects meet after passing through the convex lens. This is required because usually every point of a physical object reflect rays in different direction. So if those rays impact directly on the sensor, all the sensor will have contribution from the same point, producing a totally blurred image. For avoid this and have a very sharp image, all the different rays that comes from the same object must be blend, you see, to converge in the same point to produce a sharp image in such a way that a point in our image, in the sensor of the camera, have all the contributions, all the rays coming from the original physical point. The focal length is strongly related with the angle of view. The smaller is the focal length, the smaller is the angle of view, and vice versa. The longest is the longest, as you see here, the longest is the focal length, the shorter will be the angle of view. Sorry, I think that I have said contradictory things in this sense. I repeat, shorter focal length imply a wider angle of view, what is called usually wide angle lenses. This shorter focal length that have a wider angle can cover more scene from the real world, as you can see. On the other hand, larger focal length cover or have associated a smaller angle of view. Okay, and this is what is called typically telephoto, super telephoto, etc. This is also very related to the what is called the zoom of a camera. But it's everything about the focal length and the how much environment can you cover with that focal length. How much is the angle of view of the camera according to that focal length? You have to realize that the camera has always a specific sensor with specific resolution, a number of elements, okay? The difference is how you saw those number of pixels, those number of components in your camera sensor to cover one scene of the real world. If we have to cover a wide angle, a wide portion of the scene, you have to distribute all the pixel elements of your sensor for all that angle of view, and then consequently you have less definition. Because for every piece of object in the scene. On the contrary, if you concentrate all the pixels in a very narrow very narrow part of the scene, very narrow part of the scene, you have more definition of that specific part of the scene, what is usually attributed or called the zoom factor. Here you have an example about different focal length and different perception of the zoom, and also another close related feature that is the depth of field. We will speak more about the depth of field later. But as you can see, the depth of field is appreciated different between different focal lengths. This implies that for higher focal lengths, larger focal lengths, is more difficult to see, or is less appreciated the relative depths among the different elements that compose the scene. And on the other hand, if you have a shorter focal length, you can appreciate more the different depths among the objects that compose the scene. Here we have make a zoom of these two elements, because regarding we have said previously about the zoom and the angle of view, etc., it should be fair to say that this is a correct zoom image, but this is not related with the expected zoom. But because this is the original image, will have is more larger, should be like this, okay? But to compare the different image, we have just cut a portion of the really acquired scene in this setup. The focal length is also used, or can be used mathematically, to relate different dimensions, different distances in the scene and between the scene and the lens. For example, precisely what we are saying is that the distance from the object to the lens, can be related with the distance from the lens to the image and the own focal length, that is the distance from the lens to the principal focus, according to this formula. It's interesting to see, according to this formula, that if our objects are very far away from the lens, then this term can be removed, and then the focal length just is the distance S1, the distance between the object and the lens. This also has implications in the depth of field, in the sense that if our objects are very far away, they appear to be all of them in the same depth, in the same distance, okay? And also in the definition that have the objects in the image. If all the objects are further away, all the objects are well defined. Unlike objects that have very different depths in the image, in which, due to the limitation of the lens, only some part of the objects can be well focused and the other one will be blurred. We will speak a little bit more about this later. The focal length is also related with the size of the sensor, according to this formula. This is the size of the sensor is related with the viewing angle. A higher sensor size implies a higher viewing angle for the same focal length. Okay, we can appreciate this more easily in this picture, in this graphic, in which we see the typical curves of the viewing angle according to one focal length and for different sensor sizes. So we can see that for a specific focal length, depending on the sensor size, we have different viewing angles, and the viewing angle is higher if the sensor size is higher. There is another interesting observation from this graphic. If you see, there is a linear behavior in such a way that if we increase the focal length, we are decreasing the viewing angle, the so-called zoom factor. But there is a strange phenomena at the beginning of the focal length distances, where the curve blends, is curve. Okay, this is very interesting because if you think that for very short focal length, there is like a maximum low viewing angle surrounding the 180 degree. And in fact, this has a physical explanation. If you have a camera with a sensor size, with only one sensor, it's natural to think that the sensor can only acquire one half of the wall, one half of the hemisphere of the wall, because the camera cannot see behind itself. Okay, so for extremely wide viewing angles, the more extreme will be 180, corresponding to very short focal length, because of course the camera cannot see behind it. This viewing angle can be further increased from that figure, from that 180 degrees, with other special lenses or with the combination of different camera sensor to produce a whole panoramic or produce a 360 degrees acquisition. As we have said, the focal length is related with the concept of zoom. Varying the focal length, we have a different angle of view that produces a different zoom feeling. This zoom effect is physically obtained by integrating different mobile lenses in the optical block. The variation, the different distance among these mobile lenses allowed to change the focal length and consequently the zoom factor. In fact, the zoom ratio can be defined as the maximum and minimum achievable focal length. Usually, ratios up to 20 times can be obtained by means of optical capabilities, but higher values are not exactly due to the optical block, but are obtained by means of signal processing capabilities, what is called the electronic zoom. In the next video, we will see more relevant features about the optical block.